Section 28.7, the relativistic addition of velocities. So earlier we saw that once you start traveling super fast, we don't have the simple velocity addition, right? If the truck's moving at 15 meters per second and the ball is being thrown at 8 meters per second, then normally they would just add together. We could say, hey, the ball relative to the ground is moving at 23 meters per second. But once you start traveling at a reasonable fraction of the speed of light, this won't hold. And so that's where we need this relativistic addition of velocities equation. So this is one that's specifically designed for this scenario, right? If you want to find the speed of the ball relative to the ground, assuming that ball and the truck are moving very, very fast, you will still add together the speed of the ball to the speed of the truck. So that part is the same, but you're now also going to divide by 1 plus the speed of the ball relative to the truck and the speed of the truck relative to the ground divided by c squared. And that's how you can get the speed of the ball relative to a ground-based observer. So you're changing the reference frame of the speed of the ball. So let's see this in an example. So imagine a hypothetical situation in which the truck in the figure is moving relative to the ground with a velocity of 0.8 c, super fast. Person riding on the truck throws a baseball at a velocity relative to the truck of 0.5 c. What is the velocity of the baseball relative to the person standing on the ground? So since this is a case where we want to find the speed of the ball relative to a different reference frame, a different inertial reference frame, both the truck and the ground-based observer are inertial reference frames because they are not accelerating. So to find the velocity of the ball relative not to the truck but to the ground, we will use our velocity addition relativistic formula. So plugging in for the velocity of the ball relative to the truck, the velocity of the truck relative to the ground, we're just adding those. If that's all we did, we would end up with 1.3 c, 1.3 times the speed of light. That the ball would be traveling faster than the speed of light, which is impossible. So that's why we divide by this other term, 1 plus 0.8 c times 0.5 c. And because we're dividing by c squared, there's no reason for us to multiply out this 3 times 10 to the 8th, because c times c divided by c squared, I hope you can see that all of those c's are just going to cancel out. And so we're left with a denominator that is just 1 plus 0.8 times 0.5, which I think will be 0.40. So divided by 1.4, and so we get something that is very nearly the speed of light, but is not in fact the speed of light, 0.93 c. This is now physically possible, so we are all relieved. Relativity helped us out by not creating an unphysical situation. We could apply this relativistic formula as well to our example of the flashlight, where if we shine a light at speed c, where the person holding the light sees it moving at speed c relative to the truck, if we plug that in here, so it's moving at c, the truck still, we'll say, is moving at 0.5 c. Now we're dividing by 1 plus c times 0.5 c divided by c squared. And what do we end up with here? Well, here we end up with, on the top, 1.5 c, and on the bottom, we have 1 plus 0.5 c squared divided by c squared. So those c's are going to go away. We have 1.5 c divided by 1.5. In other words, we just get c out at the end. So that's a relief as well, because since these are both inertial reference frames, every observer should observe light traveling at the speed of light based upon our postulate of relativity. All right, so now let's take this to an example. So conceptual example, the speed of a laser beam. A cruiser, see this intergalactic cruiser down here, is approaching a hostile spacecraft. The velocity of the cruiser relative to the spacecraft is VCS is equal to 0.7 c. Both vehicles are moving at constant velocity. The cruiser fires a beam of laser light at the enemy. The velocity of the laser beam relative to the cruiser is VLC is equal to plus c. Which of the following statements correctly describes the velocity VLS of the laser beam relative to the Renegade spacecraft and the velocity v at which the Renegades see the laser beam move away from the cruiser? Right. So we have a lot to untangle here. I encourage you to think about it before we talk about it. So go ahead and think about it. So hit pause now. Right. So taking a look at this, there's a lot of terminology. It gets really confusing what speed is what reference frame is what, but we can check both the cruiser and the spacecraft are moving at constant velocity. So because they're moving at constant velocity, that tells us that they're inertial reference frames, and so both should see the laser moving at the speed of light. So we see that the cruiser observes the laser beam relative to the cruiser at the speed of light, so that checks out, and it should be the same for the laser beam as observed by the spacecraft, that this should also see it moving at the speed of light, which leaves us only C or D here, right? Because A sees the spacecraft sees the laser moving at 0.7 the speed of light, or B sees it moving even slower compared to the speed of light. And the laser needs to travel at the speed of light in any inertial reference frame. So we've already cut out half of our options, or just about, minus E, none of the above. And so then we can look at the second part, the velocity v at which the Renegades see the laser beam move away from the cruiser. So this is interesting. We have the speed of the cruiser relative to the spacecraft, this 0.7 c, and we want to compare what the spacecraft sees of the cruiser to the laser beam. So this is all from the perspective of the spacecraft. So this v here is going to be looking at how much faster the laser beam is going than the cruiser. So relative to the spacecraft's perspective, what is the speed of the laser beam relative to the spacecraft? And it's going to be compared to the speed of the cruiser relative to the spacecraft. The speed of light of the laser is going to be higher than that of the cruiser, so the laser is going to be still approaching the spacecraft, but it's not going to be moving away from the cruiser at a full speed of light c. The relative velocity of it moving away from the cruiser is just the difference in these velocities, so c minus 0.7 c. And so the result here will come out to D, this 0.3 c. Now, why didn't we need to use that equation we just got? I know, I really like that equation too. So if you're bummed, I get it. The key here is that both of our velocities that we were comparing were already relative to the same observer, to the spacecraft. So since they were relative to the same observer, we didn't need to use that extended equation. We could just directly compare the velocities to get the relative velocity difference between them. Right, and that actually pulls us through all of chapter 28. It's been quite a trip. Thanks for hanging in there for the whole ride. Let's take a look at the summary before we go. So what have we seen? We've seen time dilation, that if you start moving fast enough, time slows down, or length also contracts when you move fast enough. So you can measure this proper length in the rest frame, but from the outside, if something's moving really fast, it appears shorter. We've seen that momentum is relativistic once you start traveling really fast, and you can describe the total energy of the object in terms of a similar equation, which has the rest energy mc squared divided by the square root term. And if we combine the relativistic momentum with the total energy of the object, we can relate the total energy of the object, the momentum, and the rest energy, which is a really useful equation that will appear again for any time we have particles. This will often be important. The rest energy of an object, as mentioned, is E equals mc squared. Kinetic energy of an object is just the difference from the total energy minus that rest energy. And we have a relativistic addition of velocities. If you need to change your reference frame, you can use this equation. You'll just need to substitute in, instead of ground, maybe it's earth. Instead of truck, maybe it's spaceship. So you can totally do that. I'm happy to help. So please, as you have questions, come by my office hours, send me an email. You can also reach out to other resources like Stem Cell. We are here for you. We are happy to help. So please do get the help you need. And that is a wrap on chapter 28.